Oh yeah, and this time you don't. If you want my notes, you don't need to email me. Like I got a lot of people who wanted them. So what happens with Zoom is after the meeting ends, I get a list of all the students that came and their emails. So I'll just send it to everybody on that list, and then you can use it to study. So yeah, don't worry about emailing me for it this time. Oh yeah, and then I decided. I mean, it's kind of a ways off, but for the final, I'm gonna send out all of them. So don't worry about losing them. Uh, yeah, I'll send them all out again later. Hopefully they'll help you. Okay, I think we got a good amount of people here. I want to apologize in advance because I haven't slept since yesterday. I also haven't eaten since yesterday, and I am feeling weird. But we can probably get through this just fine. So one thing to know about this test, there's actually quite a lot less, quite quite a lot less to know. Like there are fewer concepts involved here. Last time we had 10 different problems, and almost every single one of them was a different concept. This time it's just basically two things: interest and derivatives. So problems 1 through 3 are about interest, uh, either involving payments or not involving payments. Problem 4 through 8, those are about some new derivative rules that you have. And then problems 9 and 10, those are about partial derivatives. So that's when you have more than one variable. So instead of just x, you have x and y. And what do you do in that case? Okay. All right, I think we're full. So let's go ahead and get started. Just like last time, I'm going to run through all 10 of them. If you have questions, you can just stop me. If I make mistakes, which is probably very likely, you can also interrupt me. And then at the end, I'll work any additional examples or whatever other questions y'all have. So problems 1, 2, and 3. These are all about interest. And there are two main types of interest problems that you're going to be dealing with. Ones that have payments and ones that don't have payments. And you'll be able to tell from these word problems whether there's a payment involved. So let me just show you one to show you what I mean. So first problem says a dude deposits $800 into an account. What's it going to be worth in the future? It says nothing about payments, right? So this is one of the problems that doesn't involve payments. If we look at problems 2, so look at problem 2, it says Edward invests $500 each month. Each month. That implies that he's putting $500 in each month. He's making payments. So that's going to be the second type of interest problem. Okay, and the same with problem 3. April borrows a loan, and then she wants to pay it off over the course of 5 years. So she's making payments. This is a payment problem. Okay, so that's the two types. Either you have payments or you don't have payments. It may not be in the same order on the test. But okay, let's go back to this chart. So we have two types, payment or no payment. When you have payments, that's called an annuity. So making regular payments is called an annuity. I might refer to it as that while we're talking here. But what we begin with, no payments, there are 3 different types of interest that you'll be dealing with for the non-payment problems: simple, compound, and continuous. And it will tell you in the text of the problem, it will say what it is. Like on number 1, it says continuous interest. All that means is you pick this formula, the continuous interest formula, and you will use that for the problem. So it'll specify one of these 3 types of interest for you to use. You pick it, and then you're going to plug in values and then solve for whatever's missing, whatever's asking you for. Okay, so I have a little chart here. Not entirely relevant. It might help you. This is just a graph of the different types of interest. So if we had no interest at all, the money that you put in at the beginning, that's called your principal, will just stay the same over time. It'll just have the same value throughout the entire period. And then you, at the end, it's the same. So the future value is just equal to the initial value. If you have simple interest, what that means is you dump it into an account and it'll gain interest over time. And then it'll linearly grow. And then after some amount of time, you pull out your principal and the interest. Okay. What compound means It's sort of like simple, except every now and again, where you see these dots, you you take the interest that you've earned and you stick it back in so it can earn you interest faster. Okay, so you keep increasing the amount that's earning interest, and so it kind of works its way up like this. And each time that you see each of these dots, each time that you reinvest, that's called a compounding. Like that's called a compound. So these compound. In this case, it is compounded 4 times. Or so if this was the span of 1 year, this would be quarterly compounding. And then the last thing you see is continuous. So continuous, usually better than all of them. It means that as soon as you make a cent of interest, it's going straight back into your account to help you earn interest faster. So yeah, that's the difference. Continuous, usually the best. Simple, usually the worst. But okay, so that's for non-payment problems. For payment problems, it's going to tell you that you're involving payments. It's going to ask you what the payment is, or it's going to tell you what the payment is. But it's going to involve payments. There are 2 ways to work these. I recommend your calculator. It's way quicker. You're less likely to make algebra mistakes. There's less to remember. And you're going to end up using your calculator with either one of these methods. So I just say use your calculator, use your finance apps to do these other problems. So for the annuity problems, you have either the finance apps approach, which I'll describe to you later, and then the formulas approach, which is to just use these formulas that you're given, future value or present value. That's what FV and PV stand for. The only difference between these two is what time we're talking about. So if you look at this graph down here, future value means what the loan is worth at the very end, or what your savings are worth at the very end. Like if you put a bunch of money into an IRA savings regularly, then at the end, what's it going to be worth? That's the future value. The present value, that's what it is to begin with. So if you're talking about loans, if I take out a $20,000 loan, that's what it's worth right now. That's the present value. You can also think like price tag. So if we're talking about furniture or a house or something, if a house costs $300,000, that's the present value. If you take out a loan for it, that's the present value of the loan. And then when you're done paying it off 10 years later, it's maybe 450,000. But yes, you need to know the distinction between future and present value, whether or not you use the finance apps. Okay, so if you have questions about that later, just ask me. But anyway, that should be enough background. We're going to start with number 1. So $800 is deposited into an account paying 2.5% compounded continuously. After how many years will the account have $1,000? So you can see what I've done here. I've highlighted everything that's a little piece of information. So I got $800, 2.5%, $1,000. I got the word continuous. That's telling me what type of interest it is. And I'm also told how many years. That is the question. The question being asked is how many years. So that's the quantity we're trying to solve for. And in all of our formulas, that's T, T for time. So we're given all of these values. We're told to use the continuous interest formula, and we're going to be solving for time. Okay, so that's how you break down a word problem. Just figure out all the information it's giving you. Okay, so this is the general process. First, you figure out what the formula is. It's going to tell you. Second is you're going to plug in all the values into the formula. Last thing is you're going to solve for whatever's missing. Okay, so for this problem, there's no payments. It doesn't specify any payments. So we're going to use the formula it tells us to use, which is continuous. That's A equals P e to the RT. If you know what an exponential looks like, it's that, curves up nice and smooth. That might help you remember this formula because the exponential is a very smooth, it's a smooth function. It doesn't involve like M or anything. Okay, so this is our formula. These are the values it gives us. So $800 is deposited. That's our principal. That's what's deposited at the beginning. R, that is the annual interest in decimal. That's important. Okay. So you need to know when to use this number in decimal or in percent. And there are two different cases, but we'll get to that in a second. Okay, so it tells us R, that's the yearly interest in decimal. So that's 0.025. And then it's asking after how many years will it have $1,000? So at the end of this time frame, it's going to have $1,000. That's the final value. That's A. Okay, so we have A equals PE to the RT. We're given P, R, and A. Only thing left we have to find is T. T up in this exponent here, if you can see that. Okay, so plug in the values. We have 1,800 and 0.025. Stick them all in. The issue now, okay, we're going to divide both sides by 800. We're trying to get T by itself. That's how you solve for it. But the issue now is that T is up in this exponential. T is up inside this E. So how do we get it out? And the answer is natural log, ln. Okay, so ln is the opposite of E. It will kill the E. So if you take ln of both sides, okay, on the left, you're going to get ln of 1,000 over 800. On the right, you're going to get ln of E of, all this stuff. And the ln kills the E. So all you're left with is the exponent, 0.025t. So when you take the natural log of an E, the exponent is all that remains. Okay, and you're probably going to need to know that on the test. Okay, log kills E. All right, then divide both sides by 0.025, and you have T by itself. So this is your answer. T equals log 1,000 over 800, all over 0.025. And you can simplify that. You can plug it in your calculator and get an approximation for it. 2, 3, 4 digits, it's all fine. But basically, if you get to this point, you're fine. Okay, so any questions on this one, the non-payment type problems?
Do we
No?
have to interpret always or no?
Sorry, you're kind of quiet. What was the question?
All right. Do we always have to interpret what's going on in the problem after we get the answer?
Do you always have to interpret what's going on? No. So sometimes it will ask you specifically to interpret or to like write out a sentence. For this one, it's asking how many years, just a number, just saying T equals 8.93 years, the end. Whether you include the years is completely optional. I don't think she cares. Just don't put something wrong here, like minutes. She'll probably be confused by that. So either leave it blank or have it right.
Okay, thank you.
You got it. Okay, I'm going to move on to number 2 now. So now we're getting into the payment problems. If you know how to do these, they are super quick. No algebra for you to do. You just plug it into your calculator and you're done. So Edward invests $500 each month into a Roth IRA that earns 3.2% compounded monthly. How much will be in the account 30 years from now? So again, I've highlighted everything that's important. $500 each month. So those are payments. He's making $500 payments. 3.2%, that's the annual interest rate. It's compounded monthly. So we're going to use that in our calculator too. The question being asked is how much will be in the account 30 years from now. So is that asking for a future value or a present value? Okay, 30 years from now, it's looking into the future. It wants to know in 30 years what's going to be worth. That's a future value problem. So we're going to plug into FV in our calculator in a second. And it also gives us the time, 30 years. Okay, so when payments are involved, first step is to determine whether you're dealing with future or present value, because that's going to be important for the problem. And that's just based on the context. Are we talking about what it's worth now or what it's worth later? Second step is to plug in the values that you're given. And then the last step for the calculator method is to pick one of these off the list in your finance apps, and then press enter in order to get the value. So if you're solving for the payment, you would click on TVM PMT, this option in your calculator, and it'll tell you the payment. Okay, so number 2, this one involves payments. This is an annuity problem. So we're going to use the calculator method. It's asking what it's going to be worth 30 years in the future. So that's an FV, future value problem. We take all the numbers that it gives us and we plug it into our calculator. So I trust you all know how to get there. It's on this document up here. I'll give it to you later to get to it. But it's under Apps, Finance, and TVM Solver. And you might be able to see it. So this mirrors exactly what I've written up on the screen. N, I percent, PV, da, da, da. Okay, so N is the total number of compounding periods. Okay, so if we are compounding monthly, that's 12 times a year. Okay, and we're doing it for 30 years. So the total number of periods that we compound is 12 by 30. That's 360. And in your calculator, you can just type in 12 by 30 and it'll still work. Okay, for I%, this is your annual interest rate in percentage. All right, now this is easy to remember because it has a percent right here. It says I%. Put it in as percent. Don't convert it to decimal. If you convert it to decimal, your answer will be wrong. So leave it as a percent, 3.2. Okay, this is not a present value problem, so you just leave PV blank. Just leave it blank. Payment. So we're given the payment, $500 a month. So put in 500 here. Future value is what we care about, but we don't know what it is. So you just leave it blank. Just leave it blank and you'll solve for it later. PY and CY. Forget what those are specifically stand for. I think it means like compoundings per year on the second one. Essentially, they mean the same thing. It's just your M that you have for compound problems. Okay, it's the number of times it's compounding a year. So in this case, it's 12. Okay, so once you plug all this stuff in, just leave this last option as it is by default, end. Payment is at the end of the period. Okay, so once you plug all this in, you can do second quit, and it'll take you back to your default screen. And then if you go back into your apps, finance, you can click on TVM FV. That's what we're solving for. And you get your answer. In this case, it's 301,567 and 79 cents. If there's a minus sign, just ignore it. They don't matter. So forget about the minus signs.
I'm sorry, how do you input the numbers?
Oh, okay. So let's see. So they have this, there's this like computer program where I can actually pull up a TI-84, but I don't have the money for that. So I'm just going to try and show you on the screen. So if you go to apps, finance, and TVM solver, you get into this screen. So what is your question about specifically?
That was it. I just didn't know how to edit it, like the symbols to numbers.
Oh, you're good. So once you get into this screen, you can just type directly into each one of these and then go up and down using the arrows to get to the others, and then just type in new numbers. Okay. And if y'all want a more thorough explanation, I can do that at the end. But anyway, yeah, put it all into your calculator. Is it PV or FV? Solve for what you're looking for. So yeah, once you know how to do this, it'll be very quick. Oh, someone asked me to. The answer should be 301,567,78. So I don't know. Maybe I have a rounding error here, but yeah, just round it to the cents place. So yeah, let me change that 78. Okay. Yes, I'll explain it again in 1 second. So someone asked me to show the formulas again. So right here, these are the formulas. You can find them in your book. Okay, I don't know this personally. Did she say whether you'd be given formulas for these?
Yes.
Okay, good. Yeah, so these are pretty big. These are nasty formulas. So she's going to tell you these. Okay. Let's see. Can you email? Yeah, I'll email this to everybody at the end. You don't have to give me your email. I automatically have it. Okay, so there's like some debate whether this is 7.8 or 7.9. Let me just put this in real quick and I'll make sure. So it's at 360.
What is
3.2.
PY and CY again?
I'm sorry.
What is the P over Y and C over Y again? How are you gonna?
Oh, those are like the periods per year or the compounding per year. So if it happens monthly, that means 12 times per year. So you put in a 12 here. And they'll both be the same number. So don't worry about the difference between them.
So if it were happening quarterly, you would put 4.
Yes, exactly. And I guess if it were yearly compounding, you just put 1. Okay, so give me a second. Okay, so let me solve for PVM, PMT, or future. Okay, so this is, so just ignore the minus sign once you get the number. The actual number on my calculator is 301,567.7933. And so we chop that off to 0.79. Yeah, it's the 0.79. If anything, like you would probably round it up because this is a fraction of a cent. Yeah. But yeah, I'm just going to put 79. Okay. Anyway, let's move on. So number 3 is same concept. They give you a bunch of different numbers. April borrows 15,000 at 4.75% compounded monthly to purchase a car. If the loan is for 5 years, find her monthly payments. Okay, so first step, is it future value or present value? So she's borrowing $15,000 to purchase a car. So the people that are selling her the car, they want $15,000. They want it up front. That's the present value, the price tag. Okay, so she's taking a loan out for that amount. This is PV. Okay, there are payments involved, of course. So this is an annuity problem. I'm going to use the calculator again. So PV, we're going to plug in all the values that we have. So this time we have N, the number of periods. It's monthly again. So that's 12 per year. Over the course of 5 years is 60. Okay, I percent, that's your yearly percent. Leave it as a percentage. So that's 4.75. PV, present value. So it tells us the present value. It says 15,000. That's what she's taking out a loan for. Payment and future value, leave those both blank. So this is not a future value problem, so we ignore this. And payment is what we're solving for, so you can also just leave that blank. Again, these PY and CY, that's the number of periods a year. That's 12 for both of them. Okay, and then once you put that in, you go back out and you press TVM payment. So you go to that and press enter, and you'll get the future value. Or sorry, why did I say future value? This is payment. You'll get the payment to be about $281.35 and round that to the cents place. Okay, so same procedure, just plug in a bunch of values, determine is it PV or FV, and then get what it's asking for. Okay, any questions on this one? Okay, so 1, 2, and 3, all about interest. The rest of them are about derivatives. So that's 7 questions on this test that are about derivatives. So 70% of your grade is going to be about these derivatives. So make sure you study them. I've hopefully got something that can help you here. So let's get started. Okay, number 4 through 8. These deal with new rules. We're still doing functions of x. Later on, we'll get to partial derivatives. That's when you have x and y. But for now, it's just x. And we're looking at a couple new rules that were given. So the way I think about this is we know some derivatives already. Like we know how to do the derivative of x squared, right? That's just the power rule. So we get 2x. So we know how to do that derivative. Maybe you know how to do natural log. That's just 1 over x. So the derivative of this is just 1 over x. So we know how to do these. We know how to do these things individually. Okay, pretty simple formulas. But the question is, what happens when you combine them, right? So what if I take x squared and log and I multiply them together? What's the derivative then? What if I divide them? Okay, what's the derivative now? What if I put the x squared inside of the log? Okay, now what's the derivative? Okay, so that's what these rules will help you answer. So a few things that you know the derivative of, and then you combine them in one of these ways. These rules will tell you what to do. So really what's happening is these rules are moving the derivative from something you don't know to something you do know. So if I have x squared times log x, I don't know that derivative, but using the rules, I'll end up with a derivative on just x squared and a derivative on just log x, and I know how to do those. So these rules are going to move the derivative to something that we know how to do. Okay, so I'm just gonna review them real quick. Make sure you have these down pat. You can use all sorts of mnemonics to remember them. But okay, so the product rule. If I have two functions that are multiplied together, so like up here, x squared times log x. If I have two functions that are multiplied together and I'm taking the derivative, I do first times derivative of second plus second times derivative of first. Okay, so what's happening here is I've gone from a derivative on this product, which I don't know, to a derivative on b prime, and a derivative on a. Okay, so it's turned the derivative on this to something that I know how to do. And so if you know how to do the derivative of each one of these functions, this will give you your answer. So for x squared log x, what happens is I do first times derivative of second. So that's x squared times the derivative of log, that's 1 over x. And then I do second times derivative of first. So that's log x times 2x. Okay, so each one gets the derivative individually. Okay, so quotient rule. It looks very similar to the product rule. It's just a little bit more complicated. The order here is very important. So if I have a divided by b, so a is on bottom, and I'm trying to take that derivative, it's low d high, so bottom times derivative of top, minus high d low over low squared. Okay, this is the formula. All right, and so what's done again is it's taken the derivative of this fraction, and instead now we have a derivative on the top part and a derivative on the bottom part individually. So if you know how to do those derivatives individually, then you can answer this problem. And so if we had x squared over log x, we would get this whole fraction. Okay. Now the chain rule, I think the chain rule is probably the coolest one. It's actually pretty hard to explain. But once you see it, it's going to snap in place super hard. So let me see if I can explain it. So if we have a function inside of another function, so like what if I put this x squared inside of a log? Okay, what happens then? If I have a function inside of a function, the chain rule says I take the derivative of the outside and leave the inside alone. Okay, and then multiply by the derivative of the inside. Okay, and so just like before, I've gone from a derivative on this whole thing to a derivative on a and a derivative on b. individually. Okay, so, and if I know those derivatives, I'm good. So the example here, log of x squared. So I'm going to show you a ton of chain rule examples. So this is just one of them. The derivative of the outside. Okay, so what's the derivative of natural log? That's just 1 over x. Derivative of natural log is 1 over x. So I just leave that inside there. So look at this, 1 over x squared. So the thing that's inside of log, I have 1 over that thing. That's just how logs work. Derivative of log is 1 over x. So derivative of log of stuff is 1 over stuff. Okay, and then I multiply by the derivative of the inside. So the derivative of x squared is 2x. And then I can simplify that further. Okay, but it's just derivative of the outside times derivative of the inside. And if you have a function, a side of a function, a side of a function, a side of a function, you can just keep doing it over and over and over again. You can just unwrap all the layers as many times as you want. So that makes it pretty cool. Okay, and I don't know if y'all had to use this previously, but the derivative of an exponential, so e to the x, is just e to the x. That's one special thing about exponentials is that they don't change. So when you take the derivative, stays the same. Later on, when you take the integral, stays the same. E to the x stays e to the x, whatever you do to it. Okay. Natural log, I already discussed this, but yeah, when you take the derivative of natural log, you get 1 over x. Okay, and both of these are going to be very important for the test. You're going to use both of them. Okay, so 4 through 8, these all have to do with these new rules. All these colors here might be a little bit alarming, but I'm thinking that they might be able to help you if you study this later on your own time, just to see what I'm doing. So when we have these derivatives, I want you to think about what derivatives we know. So we know how to do powers. We know how to do like x cubed, x to the fourth, so on. We know how to do natural log. Okay, we know how to do e to the x. So you got to know what we can do and what we can't do. Like the whole objective of these rules is to make the derivatives, to put them on things that we know how to do. So the first step that I always do is I just group it by what we know. You don't have to write this down, just do it in your head if you want to. So think about what we can take the derivative of. We know how to take the derivative of 4x squared minus 1. We've done that before, just the power rule. We know how to take the derivative of a log, and we know how to take the derivative of an x cubed. Okay, and one thing to notice, you have to pay attention to the structure of this problem. This x cubed is inside the log. Okay, when you have a function inside a function, we're going to use the chain rule. Also, we have this 4x squared minus 1 times this log. We have two functions multiplied together, you use the product rule. Okay, so we're going to just take this one step at a time. We just kind of look at it from the outside in. So when you're taking the derivative of this whole thing, first thing you notice is that you have two terms multiplied together. This 4x squared minus 1 times natural log. So the first thing we're going to do is use the product rule to break this up. Okay, so that's first derivative second plus second derivative of first. So if I expand this out, right, I'm going to expand this derivative out. I have the first term right here times the derivative of the second term. So that's the derivative of natural log of x cubed plus the second term times the derivative of the first term. Okay, and so I've broken this derivative of the product into these two individual derivatives here. And now they're separate. Okay, so we have two different derivatives now. To do them, we need the chain rule for the first one and the power rule for the second one. Okay, so to take the derivative of 4x squared minus 1, power rule just says 8x. Power comes down, we get 8x. For the chain rule, all right, we have natural log of x cubed. Okay, so we take the derivative of natural log, which is 1 over x, and we leave the x cubed, we leave the inside alone. Okay, so instead of 1 over x, we have 1 over x cubed here. And then we multiply by, sorry, I have these out of order. the derivative of the inside. So we multiply by the derivative of the inside here. Okay, the inside is x cubed. So take the derivative, that's 3x squared. And then if I simplify, that's 3 over x. Okay, so this is what I started with, the product rule. I then found what those other derivatives were inside. And so now I plug them back in. Okay, and so this is what I end up with. So derivative of that natural log thing, that's 3 over x. Derivative of this 4x squared minus 1, that's 8x. I put those back in, and this is my answer.
Does it matter what order you put that in for the answer? Or can you just have all of that kind of in a different order?
Oh yeah, this as long as you obey the rules of mathematics, then this is fine. So I could have the 8x out front of this. I could have this second term, I could have it be in front and then add this other one. So I can switch and swap these around all I want.
Awesome.
Sorry. You say awesome? Okay, good. Good. All right.
I had one question as well.
Oh,
Sure.
Oh, I was gonna say, for example, like the 3 over x, could we multiply that into the 4x squared minus 1, or should we just leave it?
Yes, you can do that. So you don't have to simplify on this test because
Okay.
simplifying, it just adds extra work. You only have 55 minutes. So just try and save as much time as you can.
Okay, thank you.
You got it. There's another question.
I just have a question. So you simplified like the exponents, the 3x squared over x cubed. Do we need to do that on the test? Because she said like just not to simplify, just show the derivative.
Right. Oh yeah. So yeah, I guess I just went against my own advice, but yeah, I could have it exactly like you said. So I can just leave this just like that. And that'd be fine. And so really, if you know what you're doing here, none of this work is necessary. You can just write it out exactly like this and you're done. Okay. Do you have to show that part of it or could you simply go straight to right prime? Oh yeah. So that's it. Yeah, you can just go straight to this answer if you know what you're doing. Okay, so number 5, another one of these derivative problems. There are 2 ways to do this one. One's a little bit easier than the other, but requires you to know something about logs. Okay, so we have natural log of all this stuff to the 4th power. Okay, now one common point of confusion is where are the parentheses on this? Is it natural log of all this stuff to the 4th? Like, is the 4th power inside parentheses? Or is it natural log? See if I can get that. Okay, so the question is like, what's the outside function? Is 4 on the outside or is natural log on the outside? And answer to that is, if you see a natural log without any parentheses outside of it, like everything to the right of it is inside of that log. Okay, there's another problem later where this natural log has parentheses around all of it, and then that's to the 4th. But if you're missing that second set of parentheses, just assume that the log is on the outside. That might have been confusing, but I can explain that more later if you want. Anyway, so log is on the outside. Inside of it, we have all this stuff to the 4th power. Okay. So simplest way to do this is to use the log rule. So one of the log rules is that if you have a power inside of the log, so I have this 4 right here. Okay. If I have a power inside of the log, that can come out of the log as a multiplication. So what I mean by that is if I have this 4th power inside, that comes out as a 4 in front. So that's 4 times natural log of this stuff. Okay. And then if you do that, now there's only one step, just the chain rule. Okay. Because we have all of this stuff inside of a natural log. Okay. Because it's nested, we use this chain rule. All right. So we're going to take a look at this. Natural log of all this stuff on the inside. So we take the derivative of the outside. Okay, so that's 1 over the stuff. Natural log 1 over x, right? and then times the derivative of the inside. And the derivative of the inside, we just get that from the power rule. So that's minus 2 plus 3x squared. Okay. Okay. So yeah, just the chain rule. Simple. So use the log rule to simplify it, and then use the chain rule. The other option, if you don't use that log rule, is to do the chain rule twice. Okay, so you're going to need to know how to do this later anyway. But so I have three things. Okay, I have the log on the outside. Inside of that, I have this fourth power. And then inside of that, I have the 3 minus 2x plus x cubed. Okay, so doing this, I have thing inside of thing inside of thing. All right, it's just the same process. You just repeat it. So derivative of the outside, that's 1 over stuff. 1 over the stuff inside, because it's natural log, times the derivative of the inside. Okay, and now you do the chain rule on this. Now you do the chain rule on the inside. So the derivative of stuff to the fourth power is 4 times stuff to the third power. That's just the power rule. And then the derivative of the inside, which is minus 2x plus 3x squared. Okay, so you just repeat the chain rule until you've gone all the way down to the inside. And then I simplified here. That's not necessary. You can just leave it like this second to last step as this product. That's also fine. And again, you can just go straight to the answer. Yeah, you don't need all this work. All right, so any questions about this one?
On the way
Chain
in the
rules.
second chain rule, isn't it supposed to be -2 plus 3x squared?
When you do the second chain rule. Oh yeah, I messed that up. Thank you. Yeah, copy pasted wrong. Okay. So I'm gonna keep going. All right, number 6. Number 6, we're using that exponential rule I mentioned earlier. So exponentials stay the same when you take the derivative. But you still have to use the chain rule with them if there's something up inside that exponent. So be careful for that. All right, so I'm quicker with the explanation here. We have something divided by something. So e to the 3x on top, x squared minus 5 on bottom. So we use the quotient rule. So that's low, d high. So the derivative of this e to the 3x minus high, d low. So the derivative of the bottom, all over low squared. Okay, and that's just the formula for it. All right, in order to take the derivative of e to the 3x, we take the derivative of the outside, which is the same. It stays the same. It's exactly the same. It's just e to the 3x. But we need the derivative of the inside, part of the chain rule, right? So times the derivative of 3x, which is just 3. Okay. So that's the derivative of e to the 3x. It's 3 e to the 3x. So you can also think of it as the exponent, this coefficient coming down. And then for the second part, you just take the power rule of it. So this x squared becomes 2x, and this 5 goes away. All right, and then I plug in those derivatives that I just found back in. So here's the 3 e to the 3x, and here's the 2x. And you can simplify it if you want. You can pull out the e to the 3x or whatever. Not necessary. You can just leave it like this. Okay, any questions on this one? Exponentials stay the same.
Can you pull out an e3 to the x?
Yes, you can. So you can, that's what she did in her work. So you can take out this e to the 3x and stick it out front because there's 1 in each term on top. Right. So that also works. But you can also just leave it like this if that's faster. Okay. All right, number 7. Number 7 is very short. It's just the chain rule. So like before, we have an exponential. Exponentials stay the same when you take the derivative. So if we try taking the derivative of 3e to all this stuff, the derivative of the outside is the same. It stays the same. So e to the 2x cubed minus x to the 5th. The outside derivative is e to the 2x cubed minus x to the 5th. And then we take the derivative of the inside, which is everything up in the exponent. And to find that, we just use the power rule as before. So we get 6x squared minus 5x to the fourth. And this is your final answer. You just leave it like this. Okay. So this one is the chain rule again. So on most of these, you're going to be using the chain rule. So make sure that you understand how it works. Derivative of the outside, leave the inside as it is, and then multiply by the derivative of the inside. Okay, and I got a request to go back to number 6. Did you have a question on number 6, or did you just want to see the answer?
I just want to see the different rules you used.
Okay, yeah, so quotient because it's a fraction. Chain rule because there's a 3x up inside this exponent. Right, it's not just x, it's a 3x. And then to take the derivative of x squared, you use the power rule. Got it?
Yeah.
Okay. All right, so number 8, this is the last one that's involving these new rules. Like I said before, you're going to have to do the chain rule twice, most likely. So this is the opposite of that problem I mentioned before. So before we had natural log on the outside, and then inside of that was this polynomial to the 4th power. So it was log outside, 4th power inside, and then like the x squared stuff inside of that. This time the 4th power is on the outside of everything, and that's indicated by having these extra set of parentheses out here. So make sure you know the difference between those. So chain rule, we peel back all the layers. All right, so what happens when we have a 4th power? Derivative of the 4th power, that's 4 times stuff to the 3rd power. Okay, so derivative of the outside, leaving the inside alone. Okay, and then multiplied by the derivative of the inside. And then in order to take this derivative, it's natural log of something. So we get 1 over something, right? Derivative of natural log is 1 over x, times the derivative of the inside. And the derivative of the inside, power rule, that's 5 minus 4x. Okay, so like I said before, if you know how to do this, you can just write out this string straight away. So you'd start with the derivative of the outside and then multiply by the derivative of the inside and then multiply by the derivative of the inside of that.
In your final answer, can you do 5 minus 4x over 5x minus 2x squared?
Yes, yeah, those are the same. So yeah, you can do that. Yeah. Yeah, so as long as the answers are equivalent, it's fine, whatever you write. Okay, any questions on 4 through 8? All these new derivative rules. I can spend more time on this after this session, but I want to get to these last couple problems first. Do you have to show your work? No, you can go straight to y prime. Yeah, if you know what you're doing, you can go straight to y prime. Okay, I'm going to go on to 9 and 10. So this is the last arc of the test, which is with partial derivatives. And these have a pretty simple, it's just very simple rule behind them. You just need to understand it. So partial derivatives, we have a function of 2 variables, right? So instead of just x, now we have x and y. It might, yeah, I'm going to give you an example first. I'm actually going to give you an example first because the one on number 9 is pretty complicated. So let's say we had f of x and y equals y x squared plus, let's do 3y. Okay. Now, so in order to take the partial derivatives, what we do is we look at each one of these variables individually. So we'll take the partial in x and the partial in y. And the way that works, we take the partial derivative in x, zoom in here. what that means is we just take the derivative as usual. We just take the normal derivative, except we pretend that y is a constant. And what that basically means is we ignore y in just about every sense, unless it's by itself. Okay. So if I were to just take the derivative of this, pretending that y is a constant, I would get y times 2x. Okay. So let me see if I can show that more clearly. So what I'm actually looking at here is just this x squared. So the derivative of this x squared is 2x, and I have left the y alone. Okay, and then for the second term, if we're pretending this is a constant, the derivative of a constant is 0, right? So this is just plus 0. Okay, and so your partial in x would just be 2yx. Okay, so we pretend that one of the variables is a constant. That's all there is to it. So if I were to try to take the partial in y, fy, what I'm going to do is I'm going to pretend this time that x is the constant. So x squared is the constant. Okay. And so I'm going to take the derivative of just y. So the derivative of y is 1. So I'm left with an x squared here, right? So if I had like 4y and I took the derivative, I'd just end up with 4. So if I have yx squared, the derivative is just x squared. Okay, pretending that x squared is a constant. Okay, and then the derivative of 3y with respect to y is just 3. Okay, so you just use all the same rules, all the same ideas as before, except you pretend that one of the variables is a constant. Okay, so that's the only trick there is to it. Okay, all right. So 9 and 10. 10 actually has easier work on it than 9, but we're going to start with 9, do it in order. Okay, so this is what it gives us. F of x and y is 4x cubed y squared minus 7xy to the 5th, and then all of that is squared. All right, so if you were just looking at this like it was a single variable problem, what you'd notice is that there's a square on the outside, and then there's something inside of it, right? So we have a function inside of a function. We're going to use the product rule, or the chain rule. We have something inside of something else. That's the chain rule. So we're going to be using that just like normal. Okay, so we're going to take the partial with respect to each variable individually. We're going to start with x. So when we take the partial with respect to x, that means x is our variable, and we're pretending y is a constant. Okay, so all I've done here is I've rewritten f, but I've highlighted the x's. Okay, I've highlighted those x's because that's our variable. Just pretend everything else is just hanging on for the ride. Okay, it's not involved in the derivatives. Okay, so if I take the derivative of all this stuff squared, chain rule says I get 2 times the inside, right? That's the derivative of the square, right? So 2x to the first power. And then times the derivative of the inside. Derivative of the inside is, okay, so remember, x is our variable, x cubed and x here. These are our variables. This is all we care about. So the derivative of x cubed is 3x squared. Okay, and this stuff out front, the 4y squared, that just hung on for the ride. Okay, nothing about it changed. We're just pretending it's constant. Okay, and then for the second term, we have 7y to the 5th times x. Okay, the 7y to the 5th, that's just going to hang on for the ride, do nothing special to it. So that's, the x goes away, and we're just left with the constant. Okay, and this is it. This is your f of x. This is your partial in x. f sub x. Shouldn't it be 12x squared? 12x squared. Alex, what is your question about specifically?
For like the second part of it, since it's 4x cubed and you're taking the derivative
Oh.
of that,
Oh,
wouldn't
yeah.
it be 12x squared times y squared?
Right, you're right about that. So if you notice, I have the 4 and the 3. I have the 4 and the 3
Oh,
here. Yeah,
oh,
I just
yeah.
didn't multiply them together.
Oh, okay.
Just to show you what's happening here.
Oh, okay, sorry.
No, you're good. You're good. So remember, so constants just hang on. They just hang on for the ride.
But you can multiply it, right? Or no?
Oh yeah, you can. Yeah, you can. Yeah, you can simplify it as much or as little as you want, as long as it's equivalent. But yeah, so the constants always just hang on for the ride. What's really happening here is this x cubed is turning into 3x squared. Okay, and then that 12 that you get, that's just because you multiplied it with this 4 over here. Okay, but yeah, this is just so that you could see exactly what's happening. Okay, all right, for y, it's exactly the same story. This time, y is our variable, and we're going to pretend that x is constant. So what I've done here is I've just highlighted y so you could see it. So you can see this is the variable. Everything else is just going to hang on for the ride. Okay, same as before. We have a function inside of squared. So inside of the square. So we get 2 times the inside times the derivative of the inside. Okay, and the derivative of the inside, so I have this y squared, that becomes 2y. And this 4x cubed just hangs on. Okay, then this y to the 5th power becomes 5y to the 4th power, and that 7x just hangs on. Okay. And so, yes, it's all about pretending the other thing is a constant. Just pretend the other variable is a constant. That's all there is to partial derivatives. Other than that, it's just normal. Just the same rules, the same ideas as before. Okay, and all I've done here is I've just boxed the answers so that you can see it.
In our answer, do we have to rewrite it as x going before y, or does it matter?
No, that won't matter. Yeah, multiplication does not care about the order that you're in. So xy is the same as yx. Okay, any questions about number 9? Okay, I can look at this more later if y'all want. All right, I'm gonna get to the last problem. Actually doing pretty good on time. This one is just an easier partial derivative, okay? No chain rule to deal with. So a watch manufacturer's productivity is described by this function. So its productivity is described by this function f of x and y, 50x to the 0.4 power times y to the 0.6 power. And x is labor. So remember the distinction here. X is labor, y is capital. Okay, so the idea is this. The productivity, the amount of watches that you're producing depends, 1, on how many people you have working, and 2, on like how many machines you have, like how many like sites you have to produce these watches. So people working and tools to work with, essentially. So the amount of watches that you produce is going to depend on both of those things, right? If I have more workers, that's more watches. If I have more machines, that's more watches. But the question here is, which one will give me more watches? So if I add 1 more machine, how much does my productivity go up? Or how many more watches do I make? If I add 1 more worker, how much does my productivity go up? And the one that increases my productivity the most is the one that I want. Okay, so that's the idea of this problem. We have something that depends, productivity, which depends on both the labor and on the capital. Okay, so part A says find the marginal productivity of labor and capital when 100 units of labor and 200 units of capital are used. Okay, and this is similar to a problem that you had on the last test or in like some of the previous quizzes. Marginal just means take the derivative, right? Marginal mean is derivative for our purposes, usually. And then it's asking you to plug in certain values. So it says 100 labor and 200 capital. And that's that. Okay, so we're going to take the derivatives and then plug in some values. All right, this is a 2-variable problem. So we're going to take the partial derivatives. We're going to take a derivative in x and we're going to take a derivative in y. And just like before, we pretend one of them is constant at a time. Okay, so in order to take the partial in x, right here, we pretend that y is a constant. So in other words, our variable is this x to the 0.4 power. Okay, and so when we take the derivative, all we have to do is the power rule. So what does the power rule say? You drop down the power, so 0.4, and then you reduce the power by 1. Okay, so we're going to multiply by 0.4 and then reduce the power by 1. So 0.4 minus 1 is minus 0.6. And I just did this in place. Okay, and that's your answer. You can regroup it or rearrange it however you want. You can multiply.
We just do 50. Yeah, could we just do 50 times 0.4?
Yeah, yeah. If you know what that is, you can just put that in. No problem. Yeah. So yeah, you can simplify it however you like as long as it's equivalent. And then for f of y, same process. This time our variable is y. So we just pretend everything else is a constant. It's just going to hang on. So to do this, you just drop down the power. So 0.6 times y to the minus 0.4. So you subtract 1 from the power. Multiply and then subtract 1. Same deal. So these are both of our partial derivatives. Find the marginal. Yeah. So remember what the question is asking for. It's asking for the marginal productivity of labor and capital at a specific point. So these are not your answer. It wants you to plug in values first, and then those are your answer. So if you'll notice, each one of these has an x and a y in it. So for the first one, for this f sub x, you're just going to plug in x equals 100 and y equals 200 and see what you get. So if I do that, I get about 30.3143. And what that means is we're looking at x, right? So x is labor. That means is if I get another worker, if I get another unit of labor, then my productivity goes up by 30. So 30.31. Okay. This other one, f sub y, that's how much my productivity will go up if I get one more unit of capital. So like if I buy another machine. So this says, just plug in 100 and 200, you get 22.7357. Okay, so if I get another machine, my productivity goes up by 22.73. All right, so that's the difference. Part B is like the easiest question on the entire test. Which should be encouraged? Should we increase spending on labor or increase spending on capital? Nice, clutching the test grades. But yeah, so this is the easiest question. Just do we encourage spending on labor or capital? Which one gives us more productivity? Just the bigger number, right? So a greater number means a greater increase in productivity. And so that's the one that we prioritize. In this case, it's labor at 30.3143. So this is just your answer, labor. You can also just you can also just type labor. No need to write out a sentence or anything. But yeah, okay, so that's it. That's all 10 problems. Good. If y'all have any other questions, feel free to ask me. Thank you for coming again. Sorry if that was kind of wild. I'm pretty sleepy right now, but okay, y'all are free to go if you're done. This is due by 11:45 tonight if you want 2 bonus points on your tests. So yeah, good luck tomorrow.
Okay, I actually do have a question.
Go ahead.
It's about the finance app. Like, I don't think I have that on my calculator, but I have a TI Inspire. Was I supposed to download that?
TI Inspire. Oh yeah. So I've touched TI Inspire maybe like 5 times. I know
Okay.
hardly anything about it. I'm sorry. But
That's okay. Well, so if I don't use the finance app, do I just use the like future value or present value equations and that gets the same answer? Like I'm confused a little bit on that. Like on number, I think it was like 2 maybe. Let me look. Yeah,
Oh, right.
number 2 and 3.
Okay, so let me go back up. So so
You
your question
said
about
for
like the difference between these two, using a calculator and using the formulas.
correct. Like can I use the formula instead of the calculator app?
Yes, you can.
Or
You
do
can
I
do
have
both. So the way that you use the formula, I mean, I guess I should have told you, is that so if you remember from over here, right? It gives you a bunch of
Yes.
values, and you solve for the missing one.
Mhm.
Right?
Right. Same thing on this one
Yeah, exactly.
or no?
So if it's asking for
Okay.
future value, all you do is you plug in PMT, R, M, and T. All right, so you plug in everything
Okay.
else, and it'll tell you FV. The issue is if it asks you for PMT, I mean it's slightly more complicated. So you'll plug in all the
Okay.
values and then divide both sides.
Divide and all of that. Okay.
Yeah.
I was just making sure I didn't have time to like solve it because you like kind of moved along, but I
Oh,
just wanted
sorry.
to know if that was, no, you're fine. I just want to know if that was like equivalent to the finance app.
Yeah, both of them will work just fine. I just prefer the
Okay.
calculator.
Okay. Thank you so much.
You're welcome. Also real quick, the Inspire, I'm pretty sure it has it by default. Does it not?
If it does, I don't really know how to get there. I'm on like the home page, but it has like,
Oh, okay.
I don't know. It says like graphs, geometry, spreadsheet, data and statistics. Like I don't really know what it
Yeah.
all
All right.
means.
I'll just Google it. It'll tell you like in an instant.
Okay.
But yeah,
Okay. Thank you.
thank you for coming. You have a good one.
I have a quick question really quick.
Bye.
All right, go ahead.
I submitted the practice test like 2 days ago, but I realized I had like 1 or 2 really, really minor errors, like a minus sign or a plus sign.
Oh. I think
I made comments for you where I fixed that, or do you just want me to resubmit? Do you want me to resubmit it like with it fixed, or do you just want me to leave comments and tell you like I meant to put?
as long as you know it's wrong, you're fine. So the practice test, mostly for your benefit, it's essentially a completion grade. I don't think it really looks into it. But yeah.
I had a question too. Is there any way we could go back to number 8?
Yeah. Okay. Okay. Did you just want to like look at the work?
I just wanted to see if I got that right. Yeah. Thank you. That was it. And also, are these lectures available afterwards?
Yeah. So a couple students asked me to record this one, so I can send this to you too.
Okay.
I don't want to send
I can put my
recordings.
email in the chat.
But yeah. Just give me your email and I'll give it to you.
Awesome.
It takes a while to process, so I haven't forgot about you. If you don't have it yet.
No worries. Thank you so much.
You're welcome. You have a good day.
You too.
I just had one last question, and this is just about the last test. Do you know when we're gonna get the 2 points added? from the
So I think. Oh, sorry. Go ahead.
Oh, that's all.
Okay. So I think those are kept in a separate column on the grade sheet. So what happens is it's added, but not directly to that grade. It's kept separate, but it's calculated in your final average.
Okay. Thank you.
You're welcome. All right. Thank you for coming. All right. We got any other questions?
I was just wondering if you could go over the chain rule in general, just because I get kind of confused, like when I go through it too fast.
Yeah. Okay. Sure. So chain rule, it's something it'll just click eventually. For me, it took me a while. It took me a while to understand it. Okay. Let's see if there's a better way to do this. So I'm gonna give you an example. So if I have y equals, let me get rid of all this. Let's look at something simple. So if I have y equals, that's pretty common, natural log of, like what I did before, natural log of x cubed. Okay, and I want to take the derivative of this. Okay. So let me write down the formula so that you can see it. So the chain rule formula, if I have a function inside of a function, the derivative is a prime of b times b prime. Okay, so if you just want to base this purely on the formula, then all you need to know is what a and b are. So a is log. A is your ln, right? And then b is your x cubed.
And we said the derivative of log, natural log, is 1 over x, right? So it's just 1 over x times x cubed times 3x squared.
Let's see. So here, yeah, let's look at the formula real quick. So a prime, and then you plug in b. All right, so that's actually what's happening here. A prime, and you plug in b. So this right here, this a with a b inside of it, that's a with a b plugged in. So if I have natural log of x as my a, I'm plugging in x cubed right here. Okay, so that's what a of b means. I put the x cubed inside of this natural log where the x goes.
Yeah, I'm just saying in terms of like the derivative, when you
Right.
actually do it, it would be 1 over x times x cubed.
1 over x times x cubed. So it'll be just 1 over x cubed. 1 over x cubed. And then times the derivative of the inside. So I'll show you that. So a prime, remember that's 1 over x. Let's just write it out. B prime is 3x squared. Okay. So look at this formula. So a prime, I plug in b. That's 1 over my b, 1 over x cubed, times b prime, which is 3x squared. Okay. So derivative of the outside times derivative of the inside. Like thinking about it in terms of a formula is actually kind of difficult. But I always think about it as like, what does a natural log do? So normally you have just an x inside, you get a 1 over x. So all you have in this case is that instead of 1 over x, you have 1 over x cubed. And then you multiply by the derivative of this stuff inside, which is 3x squared. I'm sorry if I'm being like too roundabout about this. Are you?
No, I get it. I get it. It's just a little more complicated with this one because you're doing natural log. I see what I was doing. I was trying to take, I was trying to make ln x like 1 over x. I was trying to do that multiplied by x cubed, but really the x is x cubed. So I see that it's 1 over x cubed as the derivative. I get that.
Right, yeah. So yeah, you just leave this wherever the x would normally be.
Okay. So if it was like 2x cubed, like natural log of 2x cubed, then it would be 1 over 6x squared.
So this?
Yeah, like the derivative of a would be 1 over 6x squared.
Let's see. So for log, right, we get 1 over the stuff. Right, so it's 1 over 2x cubed. And then times the derivative of the inside, which is just 6x squared.
Oh, okay. Yeah, I was trying to take the derivative of 2x cubed.
Yeah, you good. Yeah, so yeah, for this, you just you treat this inside part as just a unit, right? Yeah, you treat it as just one thing. just basically pretend that this is just your x, right? So you get 1 over this whole thing.
It's just 1 over whatever's in the parentheses.
Exactly. And then times the derivative of the inside.
Can you do an example that doesn't like use log or e, like
Yeah, of
just
course.
numbers?
So yeah, there's another common type, which is just y equals, like if I had 3x squared, or sorry, 3x squared plus 6x to the 4th power. So that's a pretty common one. Would this work for you?
Yeah.
Okay, cool. Let me actually, I'll leave those up here. So for this one, what do you do, for example, when you have x to the 4th? What's the derivative of x to the 4th?
It's just 4x to the 3rd.
Exactly. And so what you're going to see here is something very similar. So for the derivative of the outside, we're going to have 4 times all this stuff to the 3rd power. Okay. So we treat everything inside as if it was just a whole solid chunk. Right? We just pretend that this thing is just x, basically. So if we have x to the 4th, we get 4x cubed. Right? So that's what it means to take the outside derivative. You do whatever you normally do with a 4th power, and then just leave the inside alone.
Yeah, and then to finish that, don't you have to, yeah, you have to multiply that by the derivative of the inside, right?
Right. And what would that be?
So it'd be 6x plus just 6.
Yeah, good. Yeah, so that's exactly right.
Okay.
Yeah, so to do the outside derivative, you just, yeah, pretend this whole thing is one chunk, and then just do whatever you normally do with the 4th power.
Okay. So then, sorry, can we really quickly go to the double one
Oh, yeah, yeah.
talking about and just go over that?
Sure. So actually, what is that, number 8? Oh, is it number 8? Yeah. So we're already here.
Mm-hmm.
Okay. All right. So for this one, I probably made this like needlessly messy. I'll clean it up a little bit. But okay, we have this whole thing. It might be easier if I did an example without like logs in it, but we can just start with this. All right, so if I was trying to take this derivative.
So it's the derivative of the outside, which means the 4 is going to come to the front because the 4 is on the whole thing.
Exactly. So it's 4.
Yeah.
What happens to this stuff inside?
It's the same, right?
Yep.
For the first part. And then you're going to have 3 on the outside of it. Okay. And then you have to multiply that by the derivative of the inside. Which
yeah, the question is like, what's the derivative of the inside? So,
isn't that just, that's going to be 1 over 5x minus 2x squared. Because we just went over that.
okay. And then.
Why do you have to do it again? Like,
because there's still something inside, right? So if I were to just do this by itself, right?
oh, okay. Because the 5x minus 2x cubed is in the parentheses.
Yeah. So this is inside of something, which is inside of something else.
Mm-hmm.
Yeah. So you do it twice, right? So the outer layer, like if you think of it like peeling back layers, the outer layer is this 4th power. Mm-hmm. So you've done that. You've done that. The next layer is the natural log. Okay. So that gives you 1 over the stuff inside. And now you need the derivative of the inside this stuff.
So that would just multiply all that by 5 minus 4x.
Yes,
which is what we had.
That is correct. Good.
Okay. And then just leave that.
Yes, nice. Yeah, that's exactly how you do it.
Cool.
Right.
Okay. I think I got it.
Good. Okay.
Thank you for the help.
You're welcome.
We really appreciate it,
Good.
like the way you write it out and stuff.
Man, I hope you all do well tomorrow. Good luck. Good luck. You can
I
do
think we will. I think we will. I just make like really stupid mistakes. Like I'll just write, like in one of my quizzes, I got a 99 instead of 100 because I wrote in an extra X in the answer.
Oh,
Not
yeah.
even like I didn't even, it wasn't even in the problem. I invented it. Like I just do that kind of stuff. I'm not bad at math. I get
Yeah.
the concepts. I just do goofy things when writing it out. I don't like my brain tries to jump ahead and then that happens, but
Yeah, it's okay. As long as you have the right process. If you read the problem wrong, that's okay. As long as you got the process right, it means you know what you're doing, and you just made a little mistake.
yeah. Well, thank you so much. Really appreciate the help.
Yeah, you're welcome. Thanks for coming. You have a good day.
You too. Bye.
Bye. Oh crap, I'm still recording. Hold on, that's not good. Bye.